Okay, so let's keep talking about these distributions. Now we're going to talk about the negative binomial distribution. It's a generalization of the geometric random variable. So it's going to be the number of Bernoulli trials until the rth success, right? And geometric was until the first success occurs. Okay, so you're flipping that coin until the fifth head, for example, right? Okay, so that's our notation. Negative binomial, two parameters r and p. Okay, let's discuss the PMF. All right. So for the PMF, you're flipping that coin until the success number r, right? So the rth event has to occur at trial x. So the r is success. Yeah, we're using successes or events as synonyms. Okay, so you have one at the x, because that's the last one, right? That's when you stop tossing that coin. All right, so what that means is that in the previous n-1 trials, right? In the previous n-1 trials, we had r-1 events. So we have to have, right? So we had r-1 successes. Okay, so that's pretty much the logic. Same as the geometric, remember? In the geometric, we said that in the n-1 trials we had 0 successes, right? Now it's r-1. Okay, so the key to the understanding the negative binomial is that the distribution of these r-1 successes is binomial with parameter n-1 and p, right? Yeah, think about that a little bit. So we want r-1 successes in n-1 trials. You know, that's the very definition of binomial, right? It's the number of successes in a given number of trials. Okay, and that's pretty much it. Look, because the probability of the binomial would be this one right here with r-1, right? Go back to the PMF of a binomial, and you would see that it's r-1 here, and then this should be, right, n-1. I'm talking about this element right here. That's n-1 minus r-1, right, if you apply the binomial PMF formula. But that simplifies to n minus r, right? Okay. So that's the orange part, right? But now the last event has to be a success. So we multiply by p again, which has the effect of canceling out that negative 1 there. All right? So that's how you get the PMF of the negative binomial. Okay, and then we apply our usual formulas to get expected values and variances. All right, and here you see some shapes, typical shapes for the binomial. Right, r equals 1 here means just the geometric, right? That's the geometric random variable. But for larger r, let's say 5, you would get the red one, which is more like, it's more like a bell shape. Alright, so that's all we're going to say about the negative binomial distribution. Please take a moment to do the following example. This one right here. Alright, let's talk also quickly about the hypergeometric random variable. So in this case, we have like a urn with capital N elements, okay, in which k are a success. So we have k successes and then n minus k failures. failures, all right? And in this of this urn, you're going to sample or take n items, but without replacement. Okay, so you pick this n items, so these are your n trials, and then inside the bin there's k successes and n minus k failures. Now, this is not exactly a Bernoulli trial, right? A Bernoulli trial would be one where the probability of success is always constant, right? So that's the difference of hypergeometric. It's for finite urns, right? The capital N is, let's say, it's finite. So each time you take an element, the probability of success the next time will change, right? According to them. But the first intuition about the hypergeometric is that when capital N is infinite or very large, then it should be just like the binomial, right? Because n is so big that each time you take an element, it's not going to affect the probabilities in the future of getting a success, right? All right. So this is PMF that can be obtained using combinatorics, right? So remember. So we're going to analyze the probability that x equals I, so that the number of, right, because x is defined as the number of successes in these n trials. You see the definition is the same as the binomial, but in the binomial the trials are the Bernoulli trials. Here are these taking the elements out of this urn, right? So this probability, we use combinatorics, so it's going to be, right, the size of A divided by the size of the sample space, right? Okay, so for the size of S, and that's the probability x equals I. And the event A is the event of interest, right, is, in this case, would be x equals I. So the size of that is, you know, the length of that sequence. Okay. So for the sample space, right, so we're choosing n out of capital N. So it's n choose n like that. Right, so that takes care of the denominator. Now for the numerator, we think about the composite experiment, right? So you want to count the number of sequences in this experiment where you're going to have I successes. Okay, so the first step is choose the I successes from the potentially k successes in the urn. Right, that's how many ways you can choose these I successes from k. Right, and it should be said that I has to be less than k, right? Less than or equal for this PMF to make sense. Otherwise, the probability is 0, right? You can have more successes than there are in the bin. Okay, so first step in our composite experiment is choose the successes, and then we choose the failures, right? So we're going to have, there's n minus k failures, and you want to choose little n minus I, right? That's the remaining number of failures you need to choose. Right, so that's your PMF for the hypergeometric. And again, we have means and variances there. No need of memorizing. It's just to see how we obtain the PMF, I guess. We're not going to use this distribution very much. Anyway, but it's for it's good for you to know. All right, please go over that example. Now, my favorite distribution of all times, the Poisson random variables. They're my favorite because they're so useful in engineering. Okay. Anyway, let's go through the basics. So Poisson random variable is one that has this PMF. We're going to see why and how that comes about. Our notation is x. So letters POI means Poisson. That's the last name of the French mathematician that came up with this. The parameter is theta, and it's defined for positive numbers only. All right, and here you have how it looks for different parameters theta, 5, 10, 20, 30, right? And you'll notice that it looks a lot like the normal distribution for large thetas. And in fact, we're going to approximate the Poisson by the normal when theta is greater than 5, actually. You see that already looks quite normal. Okay, one of the defining properties of this distribution is that the mean and variance are both equal to the parameter theta. Okay? Alright, so that's the basics. The PMF and mean and variance. For the CDF, there's no closed formula. So the CDF is going to be your usual, right? X less than or equal to little x is just going to be the sum. I, let's say, from 0 to x. Yeah, it's supposed to be an x right here. Of the PMF, right? So of little p of x of I. No. So your typical CDF formula, there's no shorthand notation. But again, we can do the normal approximation. We'll see that in a minute. Okay, many times we're going to talk about Poisson processes. All right, so the word process happens because we are going to define typically the random variable like this. Okay, so what happens and what's different from all the other distributions is that now we have the time variable explicitly stated in more, right? So it's the number of events in the time interval 0t. And it's this interval that makes it a process, right? Because it's for every time t, you're going to have different random variables. Okay? But they're all Poisson with the same rate, with the same parameter. Okay, so in this context, we define what we call the rate of the process, which is not the parameter. So the rate, we're going to use the symbol lambda, and it has units, so number of events per unit time. Okay, so number of cars per hour that cross an intersection, right? That idea of flow, events per unit time. All right, and then to go from a process to the usual random variable, that's the step. It's simply that the parameter theta is lambda times t. Okay, and also since we know that expected value of x is theta, so lambda t is also the expected value of the number of events in 0t. Right, and this is a timeline showing what's happening, right? So in the interval from 0 to t, you may have events. The first event happens at t1, etc., t2 and t3. Okay, so the number of events that happen during 0t is your Poisson random variable. Now, because t can change, and it often does, we refer to it as a process. But it's just like a random variable. Okay. Now, I explained this with time because it's easier to visualize, but instead of time, you could have any dimension, right? So it could be distance t, or it could be area t, or volume, population. It's really anything that has some units. Excuse me. Okay? But for the most part, we're going to do examples in time or space, really. All right, so that's the Poisson process. Okay, so this is the meat of the Poisson distribution. It's the first fact right here. Okay, and it's the best definition I can give you. And it says that it's the limit of a binomial random variable. Okay. So yeah, that's the proof. We're not gonna do anything with it. All right. So let me elaborate a little bit on this first fact. So the notion of limit of a binomial distribution is as follows. So let's stick with the time analogy, okay? So if time goes that way, right? So in parallel, we could also show discrete time intervals and call every time interval a Bernoulli trial, okay? So I could define time intervals of length delta t, like that, and fill the whole timeline in this way, such that this would be trial n, but also is going to be time t. Okay, so depending which axis you look at. But there's a correspondence between discrete time, so number of trials, and the real time, right? Simply because we know the time interval of each trial, that each trial represents. Okay? So for example, t could be 1 year, so we're going to know the number of tornadoes in the next year. Then you could divide a year into 12 months, so delta t would be 1 month, right? And then you can say in a year it would be binomial with parameter 12, and then p is whatever the probability of having a tornado in one such month. Okay. Now, but you could have also said let's divide the year in weeks, so you would have 52 weeks. And then the probability P would be the probability of having a tornado in 1 week, right? And you see the ambiguity, right? Or the number of choices you have to discretize times are infinite. You can do it in weeks, days, seconds, nanoseconds, etc. So the Poisson random variable does away with that, and it takes delta t equal to 0, let's say. It's the limit of delta t going to 0. Right, which is convenient because then you don't need to worry about how you discretize this year, if it's months or weeks, etc. Okay? And by doing that, we remedy one of the problems of this binomial approximation, right? This discretization of the year again in months, because if you say that each month is a Bernoulli trial, it means that during 1 month you can have at most 1 tornado, either 1 or 0, right? Because that's your Bernoulli trial. The Bernoulli trial doesn't have more options. It's just there was 1 tornado or 0 tornadoes. And that's a problem because you could have a month with several tornadoes, as we unfortunately have seen recently, right? So that's the problem of the Bernoulli approximation to these time problems. That once you discretize, the main assumption would be that during one such interval, only one event can occur. Right? So that's why if you think that it's very likely that more than 1 tornado would happen in 1 month, you would divide it in weeks, for example, or days, etc. But that's the power of the Poisson distribution, right? That you don't need to discretize. It's already discretized at the finest granularity, let's say. Very good. So that really is the key of the Poisson distribution. All right. So let me try to explain this equation right here. So we have this discretization with delta t, right? So you could say that t, right, is going to be just n times delta t, right? All right, and then we're going to have, there's a expected number of tornadoes that we know. That's the parameter theta, remember? So in the case, let's say there's 3 tornadoes per year, and that this is 1 year that we're looking at. So, and this guy is going to be theta, expected value, but it also will be n times p from the binomial approximation, right? So n is, let's say, 12 months, and p is the probability of 1 tornado in a month. Okay, so this relationship holds, and it's the one that connects the Poisson and the binomial random variable. Okay, and then we say this is the binomial probability. So if we divide again in 12 months, so n is 12, and this would give us the probability of x tornadoes in 12 months. And that's the binomial distribution, right? Now, what happens is that if you express this as a function of n, and n and p, and then we take the limit as n goes to infinity, you're going to get the Poisson distribution. And that's in the next page. So please go through that proof. Let's just focus on the intuition here. And again, it's that, well, from here, you see that P is theta divided by n, right? So that's your first important equation. So we replace P by theta divided by n, and then we take the limit of n going to infinity. Right, and notice that n from this equation, right, n going to infinity is the same as delta t going to 0. They're equivalent statements, right? So that is going to be our definition, if you will, of Poisson variables. The limit of a binomial when n goes to infinity, right? So the number of trials is very large, but also by looking at this equation, p goes to 0, right? P goes to 0 as n goes to infinity. But the ratio n times p is constant and is equal to theta, right? So that's the limit we're taking. It's n going to infinity, therefore p will go to 0, but the product of n and p is constant in this, right? And again, please take a look at the proof in the next slide to see the mathematics. But that's the intuition, okay? So, this gives us a good indication of when the Poisson distribution would be appropriate. And it's one where the experiment behind it, you can express it as a binomial experiment where n is really large and p is really small. Okay, so my favorite example would be traffic accidents at an intersection, let's say. All right, why is it appropriate to model those with Poisson? Because the underlying binomial experiment has a very large n and very small p. So the experiment in this case is each pair of vehicles crossing the intersection would be a trial. All right, because you need two to cause an accident. So, and that number is very large. On a day, depending on the intersection, you can have several thousands of vehicles pass, right? And then the probability of getting to an accident is thankfully very small. So those are the two ingredients we needed, and that's why the number of accidents is typically modeled with Poisson distributions. All right, so anything that the experiment is such that n is large and p is small would give you a good Poisson random variable. All right, so please try to come up with examples for the lecture. Okay, since the Poisson is related to the binomial like that, it inherits the properties of the binomial distribution. First one is the normal approximation. Okay, so this is saying that the normal approximation should be good. And remember, for the normal, the mean, we put the mean and the variance of the distribution we're approximating. In the case of the Poisson, both are equal to theta. Okay? We're going to see the accuracy charts below. And also the sum of two Poisson variables is also Poisson, right? And that's because the sum of two binomials was binomial, if you recall. All right, and there it's also Poisson, right? X1 plus x2 is also Poisson with the sum of the rates. For the binomial, it was with the sum of the trials and with the same probability. Now it's just the sum of the rates. Right, so if you have cars and trucks according to a Poisson distribution, the sum of the total traffic flow would have also a Poisson distribution with the sum of the rates. Sorry, the parameters. Okay, so please go through this proof. And this is the normal approximation for different parameters theta. So for theta equals 1, it's not very good. For 5, it's already pretty good. And then these are excellent, right? And again, you may or may not want to use the continuity correction for small thetas. But the theory is the same. Okay, and now let's do this one that's a simple example. So we have alpha particles, right? Those appear in particle physics, I guess. We're just counting these particles, and then we know that on average there are 32 in 20 seconds, right? And that gives you your rate lambda. Okay, lambda always has units. It's number of events per, in this case, seconds. Okay, and then what's the probability that no more than 2 particles will be there in 2 seconds, right? All right, so t is 2 seconds. And that's the one that changes from question to question, so we need to be careful. Okay, so that's your 2 seconds right there, which allows you to compute the parameter of the Poisson variable, lambda t. And then we can answer any question about probability, in particular, no more than 2, so that's probably x less than or equal to 2. There's no shortcut for the PMF, or CDF, so we have to calculate each term like that. And you will get this answer. Okay, so this is a simple example just to how to compute probabilities. And in general, they're going to give you the rate, lambda. And then all you have to do is compute the parameter theta just by multiplying the two. Okay, let's do this example. Please take a minute to read. Alright, so for the first part, using the binomial distribution, so this problem is exactly a binomial, right? It's the number of faults or errors in the textbook. The probability of a faulty solution is, it says 1 over 50 questions, right? So and there are a total of 1,000 problems. So it's x, that's right here, x binomial distributed with 1,000 for n, and p is 0.02, right? All right, and then the probability that it's greater than 15, greater than or equal to 15, is this big sum, right, from 15 to 1,000. So, yeah, the problem statement, we said use an numerical method, well, from alpha or even your calculator, right? Because you don't want to do this summation by hand. All right, that's the exact answer. Now, let's do the Poisson approximation, right? Because we know when n is large and p is small, we can use Poisson as an approximation to the binomial. The thing is, we need to use the good parameter, n times p, right? Which is the expected value of the number of mistakes. Okay. All right, so in this case, we also have a big summation, right, from 15 to infinity of this formula, and again, using numerical calculations, we obtain a pretty good approximation, right? And finally, the easiest way when you don't have numerical methods is to use the normal approximation, right? Because we know the normal can approximate now both binomial and Poisson. And in this case, the normal approximation is not too bad, right? 0.87. Now remember, in the normal approximation, we simply say x is not binomial, not Poisson, but normal with the mean and variance of a Poisson distribution. Now with 0.87, I did it with theta and theta. That gave me that result. We can also do the approximation to the binomial, the normal approximation. In the normal approximation, we would say x is normal with np, right? And then np times q. And that result would tell me that the probability of x equals, right, so that gives me 0.87 as well. But this one should be really 0.868. So they're not exactly the same, but they're pretty close. All right? So yeah, this part of the question is a bonus, I guess. It wasn't asked. But whenever you see these big summations that are hard to do by hand, well, impossible, right? It's like 1,000 terms. So, and then if you don't have a calculator or a computer, then we can do all these normal approximations quite easily just by looking at the table, right? Because to do these, we can just look it up in the normal table. And you see that gives pretty good approximations in general. All right. Then, as usual, please take a look at all these. We're gonna work on them in class. Now, the next distribution is the exponential. It's related to the Poisson, as we will see in a minute. So let's start with the standard definitions. So that's the notation, expo, with the parameter lambda. That's the same lambda as the Poisson, right? So is the rate. It has units, number of vehicles per hour, for example. All right, the sample space is for all x greater than 0, all positive. That's our PMF. We've seen this guy before, right? Lambda times e to the negative lambda x. And that's how it looks like. So it's, remember the geometric? Yeah, it's almost the same shape. So these are distributions that are not bell-shaped, right? They're monotonically decreasing, like that. All right, the CDF has a nice short, formula. It's not a crazy summation as before, which is just the integral of little f of x, right? And these are the shapes right here. Okay. Mean and variances, 1 over lambda and 1 over lambda squared. All right, so those are the basics of the exponential distribution. Let's do the example later. Yeah, this is a simple one just to see how to get going, right? So here the waiting time of a customer in a restaurant has the exponential distribution with an average waiting time of 5 minutes. All right, so here they're giving you the average waiting time. So average is the same as expected value, right? So this is 5 minutes, but from the formula you know that this is 1 over lambda. So yeah, lambda is 1/5, right? Final probability that the question will have no more than 10 minutes. Okay, so once you have the lambda, really the rest is easy, right? Less than or equal to 10, so, and that's the CDF 1 minus lambda x. Okay, it's very straightforward. Now let's see the connection between the exponential and the Poisson distribution. And it's the same connection that we had between the geometric and the binomial. Okay, so in this case, we have a timeline, and here a time t is right here. So the variable x is the time of the first event. Okay, that's x. And in this figure, the first event happened after x, right? So that the probability that x is greater than t is going to be the same as the probability that y, which is a Poisson random variable with the same lambda, is 0, right? And that's for the same reasons we discussed before with the binomial geometry, right? Because this statement right here, x greater than t, means that the first event happens after t. So therefore, it's even silly to say, but it's important. It means that during 0 and t, there were no events. Okay, and this we know how to compute because that's a Poisson random variable, so that's the PMF evaluated at 0, which is e to the negative lambda t. Okay, and that's 1 minus the CDF of an exponential, right? So it means that x is exponentially distributed. So what we found here is that if you have a Poisson process of rate lambda, it means that the time between events is going to be exponentially distributed. Okay? And that's fact 4.1716 here. So the time between arrivals is a exponential random variable with mean 1 over lambda, which means that x is exponentially distributed with parameter lambda. Okay? So these two definitions are equivalent. So if you have a process and they tell you that the time between events is exponential, then it means that it is a Poisson process. And conversely, if they tell you that you have a Poisson process, then you can immediately say that the time between events of that Poisson process is exponentially distributed. Very good. And also, the exponential distribution has the memoryless property, the same way as the geometric distribution. Where's my timeline here? Well, it's not here, but it's really easy to make it. So that's time right here. And then we start at time equals 0. And then we say, okay, S is, T is going to be the present time. T is the present. Okay, and then you ask him the question, so remember X, let's interpret it as the time between events, right, of this Poisson process, like the time between earthquakes. So you start at time 0, and then all the way up to time t, there haven't been any earthquakes, let's say. Right, so you know that the time of the first earthquake is going to be after t, so that's the condition. And you're asking the question, what is the probability that it happened after t plus s? So s is kind of the remaining time, and that's t plus s. Right, so yeah, s is the remaining time. And we find the same thing as in the geometry, right, that it's going to be, so the present time cancels out, so it doesn't appear here. And it's exponential, right, because this is 1 minus the CDF of an exponential random variable. Alright, so just to recap, all that matters in the exponential distribution, whenever you know that the event hasn't happened up to time t, is the remaining time. So t is the present, right? So if it happens at time at this time. So this is x, actually. What happens is that this random variable, let's call it y, right? Y equals x minus t, right? That's for remaining time until the next event. And that guy is also exponentially distributed with the same parameter, lambda. Okay, so that's why it's memoryless. It's like at each present time, it regenerates it, right? Exactly as it was before. So this expected value, so this is really y, right? X minus t is y. But this is saying, what is the expected value of the remaining time until the next event? So the actual time x minus the present time t. Given that it hasn't happened, so that's your random variable y. So it's just expected value of y, which has the same distribution as x. So it's also expected value of x equals 1 over lambda. Okay. So this remark right here says that the exponential and geometric are the only two distributions with this property, right? So if you want to get an idea what happens with any other distribution, please go through this remark. I think it's illustrative. But so for example, you would get that t doesn't cancel out, right? This property has t on it. So that's what makes the exponential and geometric so useful in practice, right? And again, and the remaining time here until the next event, if it's not geometric or exponential, is going to be something that it's not your regular expected value of t, of x. All right. Please, let's go through this one. Yeah, so we have the life of battery is exponentially distributed with this rate, right? Because they tell you that the average time was 3,000, the average duration time, right? Oh, they gave you the parameter right away. Okay, so part A is really easy, right? Just evaluate the CDF. Let's do part B is conditional. Okay, so conditional given this. So greater than 2,500, given that the battery has lasted 2,000 hours, right? So by the memoryless property, we know that that's the same as the remaining lifetime. So in this case, the remaining lifetime is 500, very clearly, right? And therefore, it's simply this computation of x being greater than 500, no conditionals, right? And there you have it. Now, you could have done the long way, and you would have obtained the same result. So the long way is, right, this is P of A given B, and then figuring out the intersection and everything. Let me add part C. It's a typical question. So here's what is the expected value of the duration of this bulb, given that it has lasted more than 2,000 hours. So let's start. So that's the question, right? E of x, given that x is greater than 2,000. Okay. So what we know is that the remaining time is exponentially distributed, right? So it's x minus 2,000. So x minus t, remember before? That's the one that is exponentially distributed, all right? So by the memoryless property, we know that this guy, which we called y before, that expected value is just 1 over lambda. It's just the expected value of exponential random variable, right? So if the remaining time is 1 over lambda, it means that the question, which was what expected value of the lifetime of the light bulb, so that has to be 2,000, right? That's the present. plus 1 over lambda. And just because it's the remaining time that it's exponential, right? And it already lasted for 2000, so the expected value would be 2000 plus lambda.